All right, guys, I'm Nicolette, and today Brian and I are here with Karen Harper. She is the president and principal scientist at Charles River Analytics, where she's working on AI and robotics and machine interface and all kinds of fun stuff. So we're going to have a lot of fun today. Thank you so much for joining us, Karen. We really appreciate your time.
Thank you. I'm happy to be here.
So why don't you kick us off by telling us a little bit about Charles River Analytics and what you guys are working on?
Sure. So Charles River Analytics is an advanced science and technology company. We do world-class research, primarily for our U.S. government customer base, and then we transition the results of that research into interesting applications in the commercial marketplace. We're a team of multidisciplinary computer scientists and software engineers and roboticists and human factors engineers and more. We really live to find important and hard problems that we can bring groundbreaking, forward-leaning science and technology to solve. We've been in business for about 40 years, so we have decades of innovation behind us, and we're now leveraging the work that we've been doing largely in the U.S. defense sector and transitioning that to find interesting related problems in transforming healthcare, in environmental applications and humanitarian applications, and problems that we face throughout the world.
So I do want to ask a little bit about that because you mentioned medical, but just about you, how did you get here? I mean, was this a passion and a dream of yours?
That's an interesting question. Yes, I think there was clarity early in my life that engineering was the path I was going to take. Mm-hmm. Where it would lead me, I'm not sure that I knew it would be to, leading a company quite like this one, which is fascinating. So I pursued an education in mechanical engineering in Canada. I went to Memorial University of Newfoundland. Fantastic place. And then I went to graduate school at Boston University and focused in robotics and control in my graduate studies. I actually joined Charles River Analytics very soon out of my graduate program, and I've been around and grown up with this company for almost 24 years at this stage. So it's been a long haul and doing all kinds of interesting and fun, amazing things. Charles River is a place that really sort of empowers our technical staff to define their own research goals and agendas and pursue those, and provides the infrastructure around them to try and help them be successful in doing it.
Right. It's interesting. You're a mechanical engineer, right? So, but you're talking about robotics. So what do you find more interesting, the mechanical aspect or the software aspect? Because once we get into robotics, it's a really good blend, right?
It's absolutely a great blend. And obviously robots are mechanical systems that happen to do a whole lot of other interesting things as well, right? Making a robot do something useful requires a whole lot of systems engineering across the hardware, the electromechanical interfaces, and the software side in order to let it do its thing properly. So at this stage of my career, I would like to refer to myself as a systems engineer more than anything else, because I love all of it.
So Karen, you brought up some of the medical stuff that you were doing, and I believe that you guys were recently awarded a contract by the National Cancer Institute, correct? Can you talk a little bit about that?
Sure. So this is the WHISPER program that we're running for the National Cancer Institute, being run by one of our principal investigators here, Aaron Winder, and his team. And WHISPER is addressing this new trend but at the intersection of technology and healthcare, where clinicians are interested in being able to reach sort of out of the clinic in order to have more insight into long-term patient assessment and how that influences disease progression. So cancer research has lots of indications of interplay between patient behaviors, lifestyles, and health outcomes. And so what we want to try and accomplish here is to acknowledge those relationships. And in particular, in WHISPER, we're focused on this phenomenon of cancer-related cognitive impairment, or CRCI. And what that means is that patients often report a mental fog associated with cancer treatments. And how can that mental fog, or that CRCI, perhaps be managed and mitigated through different daily life activities and patient behaviors? So if cancer researchers were able to collect a mass of data from out of clinic, right? So from a large population of cancer patients, being able to collect information, not just about the cognitive impairment symptoms themselves, but about all the daily activities and personal behaviors that sort of influence the general state of the patient, then that can become a really powerful tool to build up broad population-based statistics tools that can inform the correlations between CRCI and patient behaviors. So how do you do that, right? Well, we're all, walking the world these days with all kinds of digital things, our phones, our Fitbits, our smartwatches that are collecting lots of information about our daily exercise routines and our sleep patterns and things like that. So the goal of Whisper is essentially to provide an infrastructure that allows for the collection, aggregation, and analytics of all of that information from a broad base in order to inform a statistics-based model for cancer researchers that eventually could inform clinical decisions by healthcare workers, in particular doctors, along the way. So Charles River is really building that infrastructure to collect all of that information, aggregate it, store it, and run all kinds of informatics and analytics across that information to inform that population-based statistical model.
So now, is it AI that's doing most of the research around the analytics, like coming up with, okay, these are the models we need to look at based on the progressions, or is it human and AI working together?
Yeah, it's definitely. One thing I will say about Charles River is that it's always human and AI. There is no such thing as an AI system that does not have a human user at the end of the day. So we focus a lot in human-centered computing, and in Whisper in particular, being able to collect this information, apply data science to it, which is certainly an aspect of AI, but we're not necessarily sort of pushing a lot of algorithmic context here. We're doing a lot of data science across that collection of information, and then providing that information to the cancer research groups with effective visualizations, ways for them to explore and prod at that data in useful ways to inform their model.
So we're talking about medical, but you guys, I mean, you really reach. I mean, we've got drones. You've got, I mean, I know military can work with the drones, but you've got other sort of military applications you guys are working on. And so it's kind of like an opinion, but what is the most exciting, not only for you to see happen, but like, what should we be getting excited about most, you think, that's coming next that we're kind of not seeing?
Sort of in the AI and robotics space in particular. So I think there's lots of things. And yes, military applications of autonomous systems in general, drones as an example of autonomous systems, whether they're aerial, naval, surface, underwater, or ground robotics that are operating in sort of tandem to accomplish all kinds of interesting things. So, but there are other non-military applications of that as well that we can certainly spend a lot of interesting time talking about. I think one of the most interesting things that is happening at this stage is now that we have some pretty effective robots that can do interesting things, most of them are still pretty low level on the autonomy scale, right? There's a lot of people just out there, flying their uncrewed air vehicle in a heads-up display and flying it and collecting sensor data, right? That's sort of the lowest level, but it works and it does a lot of interesting things. When we think about sort of the future of using uncrewed systems that are intelligent in lots of ways, I think the most interesting stuff happens when we interact with multiple of them and different kinds of them in order to accomplish a particular mission, right? And I'll put this in a military context just to sort of start and say that in order to execute a complex operational mission, we have aerial assets, we have ships in the sea, we have underwater vehicles, we have ground robots, we have human troops interacting with all of that, right? So the complexity of integrating these kinds of systems when they're different or heterogeneous, I think, is one of the most interesting places. And heterogeneity can come from lots of ways, right? How does the aircraft interact with the ship, the uncrewed ship on the surface, which interacts with the underwater vehicle? But heterogeneity comes in lots of other forms as well. they might be different levels of autonomy. You might have a pretty remote controlled aerial drone, for example, interacting with a autonomous ship that is capable of doing waypoint level following, but perhaps not much more. But then you go underwater where you don't have a lot of communications capability, and that system has to be a lot smarter and a lot more capable. So when you're talking about coordination and collaboration across different kinds of uncrewed systems, all of those pieces of heterogeneity come to play, right? The smart systems need to understand what the less smart systems are capable of and not capable of, being able to task and retask in interesting ways. So there's a lot more complexity to be explored when we start to integrate systems of systems of unmanned vehicles into interesting applications.
Do you think for humans, right? Well, not for humans, I should say for consumers, right? For people outside of the military. Yeah, I don't know why I said humans, but because I was thinking about the AI. But for consumers, do you think a lot of it is going to be seen first in autonomous vehicles and or logistics, meaning like you have robots at warehouses moving stuff around that are going into autonomous vehicles? Is that's where most consumers are going to see it first? You know?
Well, it's already there. Right.
Right.
Amazon has robots running mad around every warehouse that it has, right? And how smart they are and how autonomous they are, there's lots of interesting questions, right, around what that is. But there's already a huge fleet of robots operating in logistics context. There are robots in agriculture at this point, robots that are running fields and things like that. So there's a lot that's happening there. And obviously we're all watching the self-driving car. It's coming. It's coming sooner than I think I would have given it credit for. And there's a lot of interesting challenges associated with it still. But there is an immense investment in getting us to the point where we can have more autonomous capabilities with respect to self-driving cars and things. So the consumers are going to see it in lots of different ways, and they're going to see some of it on the road around them, and there's going to be a whole bunch of their life that's impacted by the robots they never see.
Do you think it's going to be more? Okay, so now we're talking about, let's just take autonomous vehicles. Do you think it's going to be more vehicle communication or like vehicle to road communication? Do you know what I mean?
That's kind of where I want to go, Brian. I would have the same question almost, because you talk about, and I think, Brian, this is what you're saying, like because Karen, you're talking about the different systems and the different levels of intelligence, right? So you've got maybe an autonomous vehicle that's super smart, but maybe it's not as smart as some other device that it needs to communicate with, right? So what is the solution then? I mean, I'm sure there's a solution in place for, a military operation to kind of connect all those, sort of, we hope, right? We're getting there. But what about on, like Brian's talking about, like the everyday human level where you've got these various devices maybe within the home and the car and somewhere else and maybe on your person and your trackers, and like how do you sync all of that if they're always going to be kind of, one's going to be smarter than the other?
Right. And
yes. Sorry, go ahead, Brian.
No, and that's sort of what I was talking about. Like, you have these various different models. Like you have this sort of like ant hive model where the cars are following the cars, so they're communicating with each other, or are they going to be communicating with the road where it's like, okay, the road knows where the vehicle is and it's communicating, so it knows. So like, how do you coordinate those things? Like, how do you really like, what's the best approach to coordinate them?
I'm going to argue it is actually all of the above. Right.
Okay.
So we are going to operate for the foreseeable future as self-driving cars come online. We're going to be in a mixed environment, right, where we have cars that are driven by computers and cars that are driven by people, right? So the car-to-car communication and the interaction between the autonomous driver and the human driver is never going to be a fully modelable interaction, right? So that autonomous vehicle has to be able to operate in the environment that it's in, that can include all kinds of different things it can talk to, right? So you're talking sort of the car to car, right? So there you can have coordinated behaviors for lane changing and things like that. But That's great if the car in front of you is another autonomous car and you understand how that works and you can therefore predict what its response is going to be. If that car is a human-driven car, you don't have any of those luxuries, right? So that autonomous vehicle still has to be fully situated in its environment. So it has to understand the road, it has to understand the signage, and when it's taking a particular exit to get where it's going in navigational context. When it hits a detour and has to replan where it's going to go, it has to understand all the rules of the road with an unpredictable human driver in the loop there, right? So everything has to be situated internal to the vehicle to a certain extent. Information can come from lots of places, its own sensors, right? It has cameras and LiDARs and all kinds of interesting things to scan its environment. And that's where the situated information comes from, right? I have a map, right? Google gave me a map. I have a GPS that tells me sort of where I am. I can route against those things and figure out where I'm going. But all of the behaviors that have to happen between here and there, how do I execute a lane change safely and not take out that human driver that's behind me? How do I not run into the back of another vehicle because I can't brake fast enough? How do I monitor what's happening behind me and don't slam my own brakes on and create other kinds of issues? All of that has to be situated based on sensor information coming into the vehicle. So we can't just count on the understanding of how everything around us is going to behave because we don't know, right? There's a whole lot of what we call situated autonomy that has to be incorporated into that vehicle in order to interact with things that are predictable and all the things in the world that are simply not predictable and never will be.
So
that sounds like a lot of
it's basically both. It's basically
like a lot of work.
Right. So it's basically the vehicle's autonomous, but at the same time, it's communicating with everything around it. So therefore, it pulls in all the data. Now, here's my question, right? How much data do we really need once we have a whole bunch of vehicles out there that are all sort of pulling at this, right? We talk about, we see a lot going on with 5G and things like that. Like, at what point is there going to be enough bandwidth to have enough data coming in and out, of a vehicle?
Yeah. So in that question, I actually might want to go back to the military for a quick second and talk about some of the major challenges that they have, right? They operate in environments where that bandwidth is not there, right? So when you put an autonomous vehicle underwater, right? You have no 5G, you have no Wi-Fi, you have no GPS, you have none of those things when you're underwater. You have this tiny little pipe of acoustic communications that allows you to operate like you're a 1996 dial-up modem land, right? And that is all that you get, right? So when you're talking about an asset that's in an environment like that, the level of smarts that it has to have on board and capable of on its own is really extreme. It has to have really high-end sensing capabilities. It has to have very smart navigational capabilities. I don't get the GPS to tell me where I am in the world, right? I have to infer that information from unreliable navigation sources and try and figure out where I am, and then figure out I probably don't have a clue where I am anymore. I better go up to the surface and get a GPS fix, and make all of those decisions smartly and in response to what it sees in the environment, right? So the reason I go to that particular context in the view of your communications question is because we have built systems that can be pretty smart given those limitations, right? Definitely. Then the question becomes, when do you want to use that particular comms pipe that you have? Right. And when we're thinking about this in a military context, it's when you see something new and different and interesting that you need to tell somebody about. Right. So underwater vehicles, they're out there, they've got high resolution sonar imaging on board them, and they can wander the world and collect all of this information. But where we're going next in that capability is to put all of the AI, machine learning driven intelligence on board that vehicle to be able to figure out what it's actually seeing at any given time in that sonar imagery, right? So I just saw something, let's say from an ocean mapping perspective, I just drove by something that looks interesting. I'm going to classify that thing based on this machine learning AI that I've got on board as a coral reef. And I'm going to have some knowledge that says I'm serving oceanography right now, and understanding what that coral reef looks like is probably pretty good. So today's AI really just sort of would drive by that and collect some of that sonar imagery, and then go back, get retrieved, get all the data downloaded, and some poor human would be wandering through all that sonar imagery to figure out what's in it, right? But now we're capable of doing that live online in the vehicle, where we can look at what's happening in the sonar imagery, say, that looks like it could be a coral reef, and then dynamically tell the vehicle, I bet somebody's going to want some more information about that. We're going to abandon our search pattern right now. We're going to go back and we're going to swim around that coral reef, and we're going to collect all the information that we can about it, so that when we're retrieved, we are producing so much useful information for that oceanographer about that coral reef. So, and again, all that is happening autonomously with no pipe to ask the oceanographer, hey, do you want me to go look at this? Do you think this thing's a coral reef? Like, none of that is there, right? So
you got to put some Easter eggs in there and be like, that's Godzilla under the water.
We've been known to plant some interesting things to find it.
Oh my goodness. Well, you know, we talk, you know, and obviously here at eDesign, we're talking to a lot of engineers, and I mean, we love to talk about the applications in the future, and we are probably going to want to hear more about your future thoughts. But you know, what about the engineers who are working right now? You know, what should they be thinking about, and how should they be, you know, how can they better create products, knowing where we're going with AI and robotics, and you know, what should they know right now?
Yeah, so you know, the speed with which AI and autonomy solutions is developing in the last decade is pretty extreme. We are in what we call the AI summer, and it is the best AI summer we've ever had, right? There's a lot of investment, there's a lot of forward progress, and it's all really exciting. So, but I would like to take that question to where some of the risks are in where we're going with respect to AI. We're building all kinds of fun and new capabilities. And there's interesting challenges that come about as we go, and where a lot of focus needs to go, not just in research, but even in acknowledging in commercial systems, all of the interesting challenges, right? So let me get a little bit more specific. Talk about a term we use called verification and validation, okay? Which is, I'm going to put this smart thing out in the world, right? And I need to accredit it. I need to know exactly how it operates, in what conditions, and where, by the way, it doesn't know what to do, right? So this is what we call verification and validation, a V&V process. And I'll talk about it in terms of autonomy systems for a second here. So autonomy systems, robots that are autonomous, include or are generally built up from systems of individual behaviors, right? And each of those individual behaviors, I'll put this in the context of an uncrewed surface vehicle that is driving on the ocean surface, and it's transiting, and it has waypoints that it wants to follow. It wants to get to that next waypoint at the right time. It has a behavior that tells us, where is that waypoint? Where am I? Am I pointed in the right direction? Am I going fast enough to make my ETA to that waypoint? That's one behavior. And that's pretty straightforward to validate and verify, right? Another behavior that would come into play there is, oh, by the way, while I'm moving in the ocean surface, there are things like icebergs around me and other vessels around me, and I need to navigate my way around those things, right? So there you get into some of those situated autonomy capabilities where you're gathering information from all of your sensors in order to figure out, oh, there's an iceberg in front of me, and it happens to be between me and my next waypoint. I need to navigate around that. Right? So now you have a behavior that wants to turn away from the iceberg, and a behavior that wants to run through the iceberg in order to get to its next waypoint, right? That's a simple example, but now imagine hundreds of different behaviors that are coming together in this particular system. And how do you deconflict between all of those things and pick what's the right thing to do at any given time, right? So in our simple example, if I want to get to my waypoint, and that's the most important thing to me, I'm going to hit the iceberg, and I'm probably not going to get there, and I'm going to fail, right? But if I want to go around the iceberg, can I just tolerate getting to my waypoint a little bit later? Integrating all of those things and understanding where those behaviors conflict, that is where validation and verification becomes really, really hard, right? Because you don't know at the outset how all those individual behaviors are going to interact with each other and conflict with each other. And suddenly you want to drive left and then you want to drive right, and you end up thrashing about in the world, and bad things happen. So validation and verification is a huge challenge as we talk about more and more AI systems coming together, and autonomous systems in particular. There's a whole other framing around that, which is around what we call explainable artificial intelligence. Well, let me stop there for a second and see if you have questions on the autonomy side before I get into XAI.
No, actually, I'm actually very intrigued right now.
Yeah, I'm following. Keep going.
Okay, so I'll put the challenge of explainable AI in the particular context of machine learning, right? So AI solutions have lots of different approaches, right? The flavor of the day happens to be data-driven machine learning, right? We throw a whole lot of data at a system, and we can automatically learn new behaviors, classification techniques, things like that out of machine learning approaches to AI. It's not the only way to do it. There is symbolic AI and all kinds of other ways that we sort of go about this. But the flavor of the day is definitely machine learning. The problem, one of the problems with machine learning is that it is notoriously opaque. It is very hard to understand after you've gone through that process what that resulting AI system has actually learned from all of those data examples that it has been given, and what it hasn't learned, by the way, right? So there's classic examples in computer vision capabilities here where things sort of get a little out of whack. And you imagine that you are training, so a system that we work with, that we've been working on with DARPA, is a smart camera system that can detect whale activity, right? In the interest of protecting marine mammals from all of our human use of the oceans. So one of the challenges that comes there is we produce all kinds of data of imagery and video that has whales in it, right? And it might be actual breaching whales with, you know, all of the fabulous whale watching, flipping tails and all of that. But often it's on the horizon and it's a small breach with a little bow, and it's really hard to see and understand sort of what's happening there, right? So we're building smart cameras that can do that. Well, if in doing that, we generate a data set to train that computer vision algorithm against that is incomplete, right? It doesn't include enough things that are whales and enough things that are not whales for us to have a lot of confidence at the end of the day that what we've generated is really a whale detector and not a whale and canoe detector. Right. As an example, right? The canoe, we didn't differentiate enough in our data set from the whale, and now our system thinks canoes and whales are the same thing, right? So there's all kinds of, and you wouldn't know that at the end of the result of the machine learning process. You would explore that and find that out in a validation and verification process, hopefully. But wouldn't it be nice if we could generate that system and then open up the black box and peek into it to sort of say, okay, given all the data that I gave you to train against, what have you actually learned and what have you not learned? So this is a whole field of research called explainable artificial intelligence, where basically we put AI systems into lots of interesting situations. And then we try to monitor and understand what they do well and what they don't do well. And we try to build narratives by poking at the AI and building sort of models of its behavior that will be explainable to a human user, right? At the end of the day, somebody is going to make a decision about what that AI is telling it. And if that AI is not trustworthy because we don't understand what it knows how to do well and what it doesn't know how to do well, we are compromising that human user's decision authority. Right? So this is a whole new field of research that is getting a lot of attention, and focusing on those kinds of problems with the way that we are really quickly putting AI systems out into the world, never forgetting that we have the obligation to look at those challenges associated with how they operate in the world.
Do you think, so a lot of, you hear a lot about people talking about quantum computing and AI. Do you think
I knew you were going to bring this up. I'm psychic.
So we were just talking about quantum computing we were talking about quantum computing the other day, actually. So, but you hear a lot about quantum computing and AI. Do you think that's also going to sort of be able to help, obviously, with the detection going, yeah, it's really a whale, not a canoe. Do you know what I mean? Or is it going to change the game that drastically when we have quantum computing? Or do we have enough processing and intelligence there in the AI to be able to do it now?
So I will admit I am not a quantum computing expert. So I'm speaking a little out of turn here. But one of the things that has supported the dramatic growth of AI and machine learning approaches to AI in particular is our accessibility to computing power. Right? It takes a lot of flops to be able to train a complex system against a large data set. And anything that allows us to continue to accelerate that and learn more faster can certainly have an impact there. So I would expect quantum computing to have some influence on that front. But again, I'm no quantum expert, so I won't speak too far outside my expertise on that.
Yeah, neither am I. I don't know what. I figured maybe you knew. She's a mechanical engineer. She's into software. I was like, hey.
Yeah. One day, maybe we'll attend to some quantum stuff. There are certainly things that are not in the Charles River bucket just yet. But,
yeah.
So one last thing before we go future and forward facing and forward looking. We talk a lot about supply chains. We deal with a lot of supply chain professionals, and a lot of the innovations you see out there are around AI and all this stuff when it comes to supply chain. So what about where is that? Where are we right now in terms of how AI is helping the supply chain become more efficient and transparent and whatnot? And where can that go?
So I think it's an excellent question, and it's certainly a very timely question in COVID times, right? Mm-hmm. Supply chains have been disrupted in lots of different kinds of ways. So at the end of the day, I consider supply chain management to essentially be a planning and optimization problem, right? Though an exceedingly complex one in many, many cases. It involves developing robust plans that can move goods from sources to consumers and potentially through incredibly complex transit networks, task networks where goods are transformed in a manufacturing process before moving along to the next point. And any component in that particular expansive network can fail at any given time. It can introduce delays into the supply chain that can have all kinds of interesting impacts. Ships stuck in the canal introduced all kinds of interesting particular challenges that was global in impact within 3 days, right? So there are some really important parts of that supply chain network that we need to understand the potential fallibilities of, right? So one program that we're working on is called Prescription, and it's work that we're doing for the Defense Logistics Agency. And what we're trying to accomplish there is to apply AI-based planning and optimization solutions by using what we call probabilistic programming and probabilistic modeling of this huge, massive network. Some of which we know, right? We know that we have to move the goods from the manufacturing plant to the airplane to the, et cetera, and then move it through road networks that could fail and any number of things like that. But there's a lot of things we don't know in that, right? There are little interactions along the way in the supply chain that might not be well represented in that network. And so probabilistic programming actually gives us an interesting way to infer connections between and dependencies and redundancies in this complicated supply chain network. So under this prescription program, we're sort of looking at global trade networks and including the disruptions to that. And that can be failures. We have a current failure that we are dealing with in the COVID vaccine distribution, right? Plant in Baltimore that went down. We lost 15 million doses of vaccine. That's a huge event that had impact on the national distribution of COVID vaccines, right? Being able to identify those failure points and ideally even predict those failure points before they can happen and the degree of influence that each failure point can have, right? So that you can focus your planning and optimization problem on building all of the redundant, contingent plans around your starting plan. If this fails, we're going to do that. If this fails, it cascades in all of those ways and we're not going to be able to achieve, the supply chain objectives that we have. So AI really has an opportunity in this space to not only do better, faster planning and developing different kinds of plans, it also has the capacity to sort of reach in and inference around the supply chain network and be able to explore it and examine it and prod it with different kinds of failures and what responses might look like there.
So then to my final and my favorite question, where are we going? Where are we going? What do you envision as the future of AI, robotics, autonomous, drones? I mean, where are we going? What can we expect one day to actually come to life for us?
Always a fun and interesting question, right? I think there is a lot, there's a lot of social context around, the power of AI and the potential of AI to change the way that we operate in the world, and that is absolutely true, right? But there are still all of these risks associated with how we use it as well, right? And not just sort of that validation and verification in the explainable AI context that I was talking about before, but we also have to understand that there are social implications to using this. Ethics of AI is a really important concept that we as technology developers have got to wrap our heads around more effectively than we have to date. As we're trying to build all of these interesting adaptive capabilities, things that we're going to put into the world and teach them how to learn, right? Well, what are they going to learn? Are they going to learn good things, or are they going to learn bad things? And how are we going to sort of understand and manage that? And I'm not talking about, 2001 Space Odyssey HAL stuff here, right? But I am talking about sort of all the steps along the way as we deploy AI. We need to understand the influence that it has in the world that we're operating in, right? So while I love to talk about, the future of AI and imagining, the Jetsons traveling about in space and on space highways and things like that, really, there's so much more concrete stuff we have to wrap our heads around as technology developers in order to do the right things with AI, the responsible things with AI, and understand when that might not be the right solution, right? And again, I'm going to come back to a core tenet of Charles River Analytics. The human is not on the wayside here by any stretch. There is not, in my opinion, a single autonomous system or a single AI system that is not intended to serve the decision-making and behaviors of a human operator at some level, right? And as long as we maintain that, then I think we have a whole opportunity, right, of what things will look like in the future.
So AI will be our partner in space, not just a thing exploring
That's
space.
right.
I mean, it is interesting. I mean, we just put, another extraordinary robot on Mars, right? That is capable. We just flew a helicopter on Mars, right? And we could say, well, that thing is fully autonomous and fully AI, and it's standing on its own. Even there, no, it's not, right? It is collecting data. It is pushing data back and forth, and that team that's at the Jet Propulsion Lab, every time they have an amazing result. I don't know if you saw the graph that came back the other day of the helicopter in flight, right? Like that is the human purpose of this. And the fact that there's a helicopter that can fly on Mars doesn't matter unless there's a human purpose for us using that, which happens to be exploration and learning. So keep that in mind, and we'll be good to go.
I agree. I didn't realize I felt the same way until you said it. I'm like, yes, I believe that too.
I'm just ready for us to get to Mars. I'm just being honest.
Is that Brian?
I said, I'm just ready for us to get to Mars.
Oh gosh.
Yeah, fair enough. Fair enough.
Yeah, Nicola, here, Karen. When are we getting to Mars? That's always the question. That's the question.
I am sorry, Brian. I don't have that particular insight. Look, I mean, things are moving fast, right? Things are moving fast in lots of ways, and what SpaceX is accomplishing, and allowing us to get more human access to space is impressive, right? Human access to Mars, I think we're still a ways away.
Sorry, Brian,
That's
to
okay.
disappoint.
That's okay. I've asked like what, like
He
3 or
asked
4
everyone now. It's
astronauts,
just
like,
become a thing now.
Yeah.
I ask everyone I think actually has a good concept of when we may get there, you know?
Yeah, getting the robot to Mars has been a decades, and we've done it a couple of times, right? We've got a few pieces there, and but that's decades of work to get that, and that is not a human life in the mix, right? So we're still a ways, I think, from getting there, and we have so much we can learn in the meantime. I mean, that is the value of these autonomous systems and approaches to AI and the sensing capabilities that we have. To be able to have something like that on the surface of Mars that we can collect data from and learn from without having to get a human there, that's an extraordinary accomplishment.
Absolutely.
For all of humankind.
Yeah, for all humankind. So Karen, thank you so much. Please tell us where we can learn more about everything that you guys are working on over at Charles River Analytics.
Great.
Where can we learn more about you?
Oh, I'm sorry, I didn't hear the question.
Okay.
Yes, so obviously you can check us out at our website at cra.com. And if I may do a quick plug, we are hiring. We are looking for smart folks who want to solve big, hard problems and do it in an environment that is agile and flexible and supportive of our employee and our employee owners. Charles River happens to be 100% employee owned, and we're a great place. So come check us out, cra.com.
Awesome. Thanks again, Karen. We really appreciate your time.
Thank you, Nicolette. Thank you, Brian. This was fun.